My next topic is to develop a technique to compute the length of the curve over some closed interval, say from A to B. Now, what I want to do, as usual, is concentrate on the ith subinterval. So take a peek at this point, and let me blow up that picture. Kind of looks like this. Now, to approximate the length of the curve, I'll connect those 2 points together with a line segment, use my differential ds, and notice what happens if I horizontally and vertically connect. I get myself a nifty little right triangle. Here is a small change in the x direction. Here is a small change in the y direction, meaning that ds squared is equal to this, just using my Pythagorean theorem. Now, massaging this, take the square root of both sides. Now, if I come in and multiply top and bottom by the small change in the x, perfectly legal, it's just a funky looking form of 0. When I bring this one downstairs inside the radical as a 1 over dx squared, cancellation, refer to that as a derivative. And I clearly see ds can be interpreted as such. If, however, instead, I multiply not by dx over dx, but dy over dy, I get a different variation on this ds. Now, unlike computing volumes and solids of revolution, I don't choose the variable integration depending on whether I rotate about a horizontal or vertical line. I do it solely in terms of which one's easier to deal with. Now, this is merely ds. This is merely ds. To actually sum these together, then take the limit of the Riemann sum, it tells me that the length of a curve, as long as I have continuity, nicely behaved function, can be interpreted as the evaluation of this definite integral, where in the integrand's position, I have this radical expression. But again, I have a choice. And I would typically choose whichever version gives me an easier integral to actually evaluate.